What if the same forces that govern the tiniest particles in your phone also sculpted the birth of galaxies? This isn't science fiction. It's the startling reality where quantum mechanics and the cosmos collide. Picture this: a single electron spin here on Earth could be entangled with a star's behavior light years away. Black holes might not just devour matter, they could birth quantum particles in their final moments. Even the empty void of space isn't truly empty, but a seething quantum foam where universes might flicker in and out of existence. Over the next 15 revelations, we'll decode how the microscopic rules of quantum physics orchestrate cosmic-scale phenomena. You'll discover why particles can teleport across stellar distances, how the Big Bang left quantum fingerprints in today's universe, and what black holes teach us about the nature of reality itself. This journey will change how you see everything from the screen in front of you to the farthest reaches of space-time. Because when we peer deep enough, the universe reveals its greatest secret. There's no difference between the very small and the incomprehensibly vast. They're two sides of the same quantum cosmic coin. Einstein famously dismissed it as spooky, this bizarre phenomenon where two particles, no matter how far apart, remain mysteriously linked. Change one and its partner reacts instantly, as if space and time don't apply. But what if this quantum entanglement isn't just a tiny scale quirk? Imagine it operating across cosmic distances, like threads stitching together the very fabric of the universe. Scientists now suspect these invisible connections might explain why distant galaxies move in eerie harmony, as if guided by some hidden choreography. Even more tantalizing, some theories suggest dark matter, the elusive glue holding galaxies together, could be part of this quantum network. Picture an unseen lattice of entangled particles spanning the cosmos, whispering to each other across billions of light years. Recent experiments with quantum satellites hint that entanglement might scale up far beyond lab conditions, potentially shaping the largest structures we see in the night sky. It's as if the universe began as a single, entangled quantum state, and those primal connections never truly broke, just stretched into the vast cosmic web we observe today. Now consider the cosmic paradox of black holes, regions so dense that not even light escapes. Yet at their edges, something remarkable happens. Heisenberg's uncertainty principle, which tells us particles can't have perfectly defined positions and speeds simultaneously, becomes the key to unraveling one of space's greatest mysteries. Picture the event horizon of a black hole, where gravity is so intense it warps the very fabric of reality. Here, quantum uncertainty doesn't just influence particles, it twists the rules entirely. Empty space seethes with fleeting pairs of particles popping in and out of existence, as the uncertainty principle allows. Normally, these pairs annihilate instantly. But near a black hole's edge, gravity can yank them apart, flinging one particle inward while the other escapes as radiation. This eerie process, predicted by Stephen Hawking, reveals that even the universe's most voracious monsters aren't eternal. They slowly leak energy, sometimes called Hawking radiation, proving quantum mechanics governs them too. Think about the implications. A black hole's terrifying grip isn't absolute. Quantum uncertainty softens it, allowing particles to wriggle free over eons. Measurements show this radiation carries information about what fell in, suggesting black holes might not be the information-destroying pits we once imagined. Instead, they could be cosmic translators, encoding quantum data into their outgoing whispers. It's as if the universe built a fail-safe into these gravitational behemoths, ensuring even they play by quantum rules. Deep inside every star, a silent quantum rebellion takes place that defies classical physics. At the core of our sun, protons should never overcome their natural repulsion, like two magnets pushing apart with impossible force. Yet somehow, hydrogen nuclei fuse into helium, releasing the energy that lights our world. The secret quantum tunneling, where particles cheat the cosmic rulebook by vanishing through barriers as if they weren't there. Think of it as a cosmic Houdini act. Particles don't have definite positions, just probabilities, allowing them to occasionally materialize on the other side of an energy barrier. Without this subatomic sleight of hand, stars would fizzle before ignition, leaving the universe cold and lifeless. But the story gets stranger when we scale up to neutron stars, stellar corpses so dense that a teaspoon of their material weighs 1 billion tons. Here, quantum tunneling doesn't just enable fusion, it distorts matter itself. Protons and electrons get crushed into neutrons, creating a superfluid where particles flow without friction, tunneling through each other effortlessly. Some theories suggest these extreme environments might even harbor quark soup, where tunneling allows fundamental particles to swap identities. It's a vivid reminder that the quantum rules shaping atoms in your body also forge the furnace of every star you've ever seen, bridging the microscopic and cosmic in one breathtaking phenomenon. Light doesn't play by the rules we expect. It's both a wave and a particle, flickering between identities like a cosmic shapeshifter. But this wave-particle duality isn't just some laboratory curiosity confined to photons in a beam of light. It echoes across the universe in the most unexpected places, even in the high-energy cosmic rays screaming through space at nearly the speed of light. These aren't just random bullets fired from distant supernova or black holes. They're quantum travelers carrying secrets about the fabric of reality itself. When these ultra-fast particles slam into Earth's atmosphere, they don't just crash, they create cascades of secondary particles that somehow retain wave-like interference patterns, as if the entire universe is running a quantum experiment on a galactic scale. What's truly mind-bending is that these cosmic rays, some of which have journeyed for millions of years, still exhibit behavior that should be impossible for mere particles. They interfere with themselves like ripples in a pond, proving that even at cosmic distances and energies, quantum weirdness persists. It's as if the universe refuses to let go of its dual nature, no matter how vast the stage becomes. And here's where it gets even stranger. If these particles can behave as waves across such incomprehensible distances, could entire stars or galaxies be subject to the same quantum rules? Some theorists speculate that dark matter might even be a kind of quantum wave stretching across the cosmos, influencing gravity in ways we're only beginning to grasp. The same principle that lets an electron exist in multiple places at once might also be shaping the largest structures in the universe. So next time you see a streak of light in the night sky, whether it's a meteor or just a passing satellite, remember, you're witnessing a universe that doesn't neatly divide itself into particles and waves. It's all connected, from the smallest photon to the most energetic cosmic ray, all dancing to the same quantum tune. Think of space as a calm ocean, but peer closer and you'll find a turbulent quantum sea bubbling beneath the surface. What we call empty vacuum is anything but. Quantum mechanics tells us that even in the deepest void, particles and antiparticles flicker in and out of existence too quickly to measure directly. These aren't just mathematical quirks, they're real fluctuations with measurable consequences, like tiny ripples in spacetime itself. Now, here's where it gets cosmic. These quantum ripples might hold the key to one of the greatest mysteries in modern astrophysics: dark energy. That's the mysterious force causing the universe not just to expand, but to accelerate its expansion. Some theorists suggest these vacuum fluctuations could be pumping energy into space itself, like an unseen engine driving galaxies apart at ever-increasing speeds. Picture it like this: every cubic centimeter of space, no matter how empty it seems, is a seething foam of quantum activity. And because there's so much space in the universe, vast, unimaginable stretches of it, the collective effect of these tiny fluctuations could add up to something enormous. If this hypothesis holds, dark energy wouldn't be some exotic new force, but rather the accumulated hum of quantum noise written across the cosmos. Yet there's a catch. When physicists calculate how much energy these vacuum fluctuations should contribute, the numbers are catastrophically large, enough to rip atoms apart instantly. Clearly, reality doesn't match the naive prediction. So either we're missing a crucial piece of the puzzle, or the universe has a hidden mechanism that cancels out most of this energy, leaving behind just a faint whisper, the dark energy we observe today. This leads us to another staggering possibility. What if the universe is fine-tuned, that the balance between quantum foam and cosmic expansion isn't accidental, but necessary for existence itself? It's a question bridging the infinitesimal and the infinite, proving once again that the quantum rules governing particles in a lab might also be the invisible hand shaping the fate of everything. At the heart of quantum mechanics lies a profound mystery. Why don't we see quantum weirdness in everyday life? Why does the moon hang reliably in the sky rather than exist as a blur of probabilities? The answer might lie in a process called decoherence, and it could be the very reason our universe looks so crisp and definite today. Picture the early cosmos like a quantum soup, where every particle existed in countless possible states simultaneously. But something happened to collapse those possibilities into the concrete reality we now observe. Decoherence suggests that when quantum systems interact with their environment, whether it's other particles, radiation, or even gravitational fields, their delicate superposition states get scrambled like waves crashing against a rocky shore. Over time, these interactions force the infant universe to choose definite states, transforming a hazy quantum landscape into the sharp cosmic structures we recognize. But here's where it gets even more fascinating. Some theories propose that cosmic inflation, the universe's explosive early expansion, acted as a kind of quantum microscope, stretching tiny quantum fluctuations into the seeds of galaxies. Those primordial wrinkles in space-time, once subject to the same fuzzy probabilities as electrons in an atom, became frozen into the cosmic background radiation we now observe. It's as if the universe started with a quantum roll of the dice, and decoherence locked in those results, etching them across the heavens. This raises a tantalizing question. Could the same process explain why we don't see quantum effects on large scales today? Think of a single photon behaving as both a wave and a particle until it hits a detector. Now imagine that same principle applied to entire stars before decoherence kicked in. The mind reels at the thought of a cosmos where planets and galaxies existed in multiple places at once, until the universe's increasing complexity forced them to pick a side. Perhaps the most startling implication is that decoherence might be why time itself appears to flow in one direction. In quantum terms, time is reversible, but decoherence introduces an arrow, like an invisible hand pushing the universe from possibility to actuality. So when you gaze up at the night sky, you're not just seeing distant stars, you're witnessing the end result of an ancient quantum transition, where the hazy rules of the very small gave way to the stark clarity of cosmic structure. And that means the universe we know might just be one possible version of reality selected, but not necessarily inevitable. Ever wonder how the universe grew from a subatomic speck to cosmic vastness in less than a blink? The answer might lie in a quantum field eerily similar to one we've already discovered, the Higgs field. You know it as the cosmic molasses that gives particles their mass, but imagine a primordial cousin of this field acting like a cosmic accelerator pedal, inflating space-time faster than light itself. This is the wild symmetry at play. The same quantum mechanics that explains why you have mass might also explain why the universe has size. Think of cosmic inflation like a phase transition, similar to water freezing into ice but happening to space-time itself. Just as the Higgs field froze into its current state, giving particles mass, an inflation field may have temporarily locked in a supercharged configuration, stretching the fabric of reality exponentially. Then, like a boiling pot settling, it released that pent-up energy as the hot soup of particles we call the Big Bang. The parallels are uncanny. Both fields emerge from quantum rules, both shape the fundamental properties of reality, and both left fingerprints we can still detect today. While the Higgs field's imprint shows up in particle collisions, inflation's signature is written in the cosmic microwave background, the afterglow of creation. Here's where it gets even more intriguing. Some theories suggest these fields aren't just analogous, they could be different faces of the same underlying quantum tapestry. The same mathematics describing the Higgs mechanism also pops up in models of inflation, hinting at a hidden unity. If true, it would mean the forces governing the tiniest particles didn't just accompany cosmic evolution, they actively sculpted it. Every galaxy, every star, every atom might owe its existence to a quantum field fluctuation that got locked in during the universe's first trillionth of a second. This connection raises a profound question. Are we seeing separate phenomena or different scales of the same quantum reality? The Higgs field operates on subatomic scales, while cosmic inflations shape the entire observable universe, yet they may be branches of the same theoretical tree. It's a reminder that when we peel back the layers of reality, the distinction between particle physics and cosmology starts to blur. The very forces that dictate how particles behave in a lab might also hold the blueprints for the cosmos itself. Every time you flip a coin, the universe splits in two. At least, that's one interpretation of quantum mechanics taken to its logical extreme. The same principle that allows an electron to spin both clockwise and counterclockwise until measured might also apply to reality itself. Imagine our universe as just one page in an infinite cosmic library, where every possible quantum outcome gets its own volume. This isn't science fiction, it's the multiverse hypothesis, where superposition isn't confined to particles but stretches across entire timelines. Take Schrödinger's famous thought experiment with the cat alive and dead simultaneously until observed. Now scale that up to universal proportions. In one branch of reality, a quantum fluctuation led to a slightly denser early universe, birthing galaxies in a different configuration. In another, dinosaurs never went extinct, and in yet another, you made that left turn instead of a right last Tuesday. The math suggests these alternate histories aren't just fantasies. They could be as real as the world you're experiencing right now, separated only by an unfathomable quantum divide. What's truly mind-bending is how this idea connects to cosmic inflation. Just as quantum jitters during inflation seeded galaxies, those same fluctuations might have spawned bubble universes with entirely different physical laws. Some could have stronger gravity, making stars burn out in seconds. Others might lack dark energy, causing them to collapse moments after birth. Our universe's finely tuned constants, like the strength of electromagnetism or the mass of electrons, could simply be the numbers that survived the quantum lottery, with countless other versions playing by different rules. Critics argue this seems untestable, but clues might hide in the cosmic microwave background. Strange anomalies in its temperature patterns, like cold spots spanning vast distances, could be bruises from collisions with other bubble universes in the multiverse's foam. Others suggest black holes might be portals to these alternate realities, their singularities warping spacetime so severely that quantum superposition becomes macroscopic. While definitive proof remains elusive, the mere possibility reshapes how we view existence. So the next time you face a choice, remember, according to quantum mechanics, there's a version of reality where you pick differently. The universe doesn't eliminate possibilities, it embraces them all, weaving an endless tapestry of what-ifs. And that means the stars above aren't just distant suns, they're part of a single thread in a grander cosmic fabric, where every quantum decision spawns new worlds. Deep within the collapsing heart of a dying star, ghostly particles perform a quantum ballet that could rewrite our understanding of cosmic destruction. These are neutrinos so elusive that trillions pass through your body every second without a trace. But when a star goes supernova, they become the universe's most critical messengers, shape-shifting between three flavors: electron, muon, and tau, mid-flight like cosmic chameleons. This phenomenon, called neutrino oscillation, isn't just a subatomic curiosity. It's the hidden key to why stars explode asymmetrically, why our universe is made of matter rather than antimatter, and how quantum quirks steer stellar apocalypses. Picture a supernova's core. Temperatures reach 100 billion degrees as gravity crushes atoms into a neutron star or black hole. Under these extreme conditions, neutrinos aren't passive bystanders, they're the dominant force, carrying away 99% of the dying star's energy. But here's the twist: as these particles race outward through layers of stellar material, their quantum identities flicker. An electron neutrino born in the core might morph into a tau neutrino by the time it escapes, altering how it interacts with the star's matter. These oscillations act like a quantum feedback loop, influencing shock waves that tear the star apart. Recent simulations suggest this flavor switching might explain why supernovae blast their debris in lopsided jets rather than perfect spheres, a fingerprint of quantum mechanics sculpting cosmic-scale destruction. The implications stretch even further. Neutrino oscillations could hold clues to one of physics' greatest puzzles. Why does our universe have more matter than antimatter? According to quantum theory, the Big Bang should have created equal amounts, which would have annihilated each other, leaving nothing but light. Yet here we are. Supernova neutrinos might reveal how nature tips the scales. When these particles oscillate, theory predicts they could behave slightly differently than their antimatter counterparts, a phenomenon called charge parity violation. Over billions of years, even a tiny asymmetry could have allowed matter to dominate. Detectors buried deep underground, like Japan's Super Kamiok, and have already caught neutrinos mid-oscillation from cosmic rays and distant supernova. Each detection paints a clearer picture of how quantum rules govern not just particles, but the fate of galaxies. What makes this truly astonishing is the scale shift. A particle so small it barely interacts with anything can, through sheer numbers and quantum metamorphosis, determine whether a star dies with a whimper or a bang, and by extension, how heavy elements like gold and uranium get forged in those explosions. Without neutrino oscillations, the periodic table might be half empty, and planets like Earth might never have formed. So next time you spot a twinkling star, remember, its eventual death throes will be choreographed by particles that refuse to stay in one quantum identity, proving once again that the universe's grandest events hinge on its smallest rules. Gravity shapes the cosmos, bending starlight around galaxies, sculpting black holes, even slowing time itself. Yet down at the quantum level, this force becomes an enigma. Einstein pictured gravity as the smooth curvature of spacetime, like a trampoline sagging under a bowling ball. But quantum mechanics insists everything comes in discrete chunks: energy, charge, even information. So what happens when these two frameworks collide? The answer might rewrite our understanding of reality itself. Imagine spacetime not as a seamless fabric, but as a shimmering mosaic of quantum pixels, each 100 billion times smaller than an atom. In this radical view, wormholes, those fabled cosmic shortcuts, could form naturally from the frothy quantum vacuum. They'd flicker in and out of existence too quickly to traverse, stitching together points in space like temporary quantum stitches. Some theories suggest these microscopic tunnels could solve black hole paradoxes, allowing information to escape what was thought to be an inescapable prison. The implications ripple outward. If spacetime has quantum structure, the extra dimensions predicted by string theory might not be abstract math. They could be curled up at these unimaginably tiny scales, like origami folds in the fabric of reality. Experiments aiming to detect spacetime's quantum graininess look for subtle blurs in high-energy particle collisions, or hunt for delays in gamma rays traveling across the universe. Even gravitational wave detectors might one day catch whispers of these spacetime pixels as black holes merge. Perhaps most astonishing is how these ideas bridge vastly different scales. The same quantum gravity effects that could spawn wormholes might also explain why the universe didn't collapse instantly after the Big Bang. Tiny spacetime fluctuations may have provided just enough repulsion to keep infant cosmos inflating. It's as if the universe's grandest structures, black holes, galaxies, even the cosmic web, owe their existence to quantum gravity's delicate balance. So when you gaze at the night sky, you're not just seeing stars. You're glimpsing the emergent pattern of countless quantum threads woven together across the loom of space-time. The cosmic microwave background isn't just a relic of the Big Bang, it's a quantum fossil, preserving the faintest tremors from the universe's first moments. Those subtle temperature variations you see in maps of the CMB, they're not random noise. Each hot and cold spot represents a quantum fluctuation stretched to cosmic proportions during inflation, like microscopic wrinkles magnified into mountain ranges by the universe's explosive expansion. What began as subatomic shivers in the quantum foam became the gravitational seeds for everything we see today: galaxies, clusters, even the vast web of dark matter connecting them all. Here's the astonishing part: the patterns in this ancient light match predictions of quantum mechanics with eerie precision. The distribution of those fluctuations follows a statistical fingerprint called Gaussian randomness, exactly what you'd expect if quantum uncertainty got baked into spacetime itself. It's as if we're staring at a snapshot of the universe's quantum adolescence, frozen in time when the cosmos was just 380,000 years old. Modern telescopes like Planck have measured these variations down to millionths of a degree, revealing a curve that aligns perfectly with quantum field theory. But the real magic lies in the scale shift. Those primordial quantum jitters were unimaginably tiny, smaller than a proton across, yet inflation, acting like a cosmic zoom lens, blew them up to megaparsec scales. Gravity then amplified these subtle density differences over billions of years, sculpting them into the galaxies we observe. Without quantum mechanics' inherent randomness, the universe might have remained featureless, a cold, uniform soup of particles with no structure to spark star formation or planetary birth. This raises a profound question. Could the CMB hold clues to quantum gravity? Some theorists hunt for anomalies in its polarization patterns, swirls that might betray how spacetime itself behaved quantum mechanically during inflation. Others speculate that faint non-Gaussian signals could reveal interactions between unknown quantum fields active in the universe's infancy. Either way, the CMB isn't just light, it's a palimpsest written in quantum code, and we're only beginning to decipher its deepest layers. So when you see static on an old television, remember, about 1% of that snow comes from the CMB. You're literally witnessing quantum fluctuations from the dawn of time, translated into electromagnetic whispers after 13.8 billion years. The same physics governing electrons in silicon chips also orchestrated the cosmos, proving once again that quantum mechanics didn't just accompany creation. It was the composer. In the coldest corners of the universe, quantum physics performs its most delicate magic, Take a cloud of rubidium atoms chilled to just billionths of a degree above absolute zero, so cold that individual particles lose their identities, merging into a single quantum wave called a Bose-Einstein condensate. This isn't just laboratory curiosity. It's matter in its most cooperative state, where atoms march in perfect unison like a cosmic ballet frozen in time. Now stretch this phenomenon across light years, and you might uncover one of cosmology's deepest secrets. Dark matter could exist in a similar quantum state, hovering between particle and wave on galactic scales. Picture a vast halo of dark matter enveloping a galaxy. Instead of behaving like individual particles crashing about, it might flow as a coherent quantum fluid, its wave-like nature allowing it to pass through itself without friction or collision. Some theories suggest certain types of dark matter, like actions or ultralight particles, could naturally form these cosmic-scale condensates. The mathematics reveals eerie parallels. Just as lab condensates exhibit quantum interference patterns, dark matter's gravitational effects might bear the signature of wave-like behavior. Computer simulations show that when you model dark matter as a quantum fluid rather than discrete particles, it naturally clumps into the filamentary cosmic web we observe, something traditional cold dark matter models struggle to explain perfectly. The implications are staggering. If dark matter forms Bose-Einstein condensates, it could solve multiple cosmic puzzles at once. Galactic rotation curves, which show stars orbiting too fast at the edges of galaxies, might make sense if dark matter isn't just invisible mass, but a quantum wave exerting subtle pressure. Even the mysterious cores of dwarf galaxies, which appear less dense than simulations predict, could fit this model, as quantum effects would prevent dark matter from collapsing too sharply. Here's where it gets truly mind-bending. If dark matter exists as a quantum condensate, it might exhibit properties we've only seen in microscopic systems like superfluidity. Imagine an invisible, frictionless river flowing between galaxies, or dark matter vortices spinning at the hearts of galaxy clusters like quantum whirlpools. Some researchers even speculate that dark matter's quantum coherence could create interference patterns detectable through gravitational lensing, subtle ripples in spacetime itself. While definitive proof remains elusive, the overlap between ultra-cold quantum experiments and cosmic-scale mysteries grows harder to ignore. Laboratories creating Bose-Einstein condensates here on Earth might be simulating, on a tiny scale, the very physics governing the universe's largest structures. It's a humbling thought. The same quantum rules that make atoms merge into superfluid blobs in a vacuum chamber could also dictate how dark matter sculpts the cosmos. And that means the key to understanding the universe's hidden skeleton might not lie in gigantic telescopes alone, but in the delicate dance of particles cooled to near absolute zero. Inside a black hole, time doesn't just slow down, it might shatter into quantum fragments. Near the singularity, gravity becomes so intense that Einstein's classical spacetime bends until it breaks, leaving only a storm of quantum uncertainty. Here, the steady tick of clocks we know gives way to something far stranger. Time itself could become probabilistic, flickering between possibilities like a cosmic stopwatch stuck between ticks. This radical idea suggests that what we perceive as the smooth flow of time might not be fundamental at all, but rather an illusion emerging from deeper quantum interactions, like how temperature arises from the motion of countless molecules. Picture throwing a clock into a black hole. From the outside, time dilation makes it appear to freeze at the event horizon, hands crawling infinitely slow. But inside, past that point of no return, the clock doesn't just stop, it loses its very definition. Quantum gravity theories propose that near the singularity, space-time might dissolve into a foam of fluctuating geometries where before and after cease to have meaning. Instead of a single timeline, you'd have a superposition of temporal states, all coexisting until some unknown quantum process resolves them. It's as if the universe hits a quantum glitch, corrupting the file labeled time at the black hole's core. This could answer one of physics' biggest headaches, the singularity problem. Classical relativity predicts an infinitely dense point where spacetime curvature becomes infinite, a nonsensical result signaling the theory's breakdown. But if time becomes quantum mechanical, that infinity might smooth out. Imagine zooming in on a pixelated image until you see the individual grains. Similarly, quantum time could reveal spacetime's underlying granularity, preventing true singularities. Some models suggest black holes might not end in a point of infinite density, but in a fuzzy quantum bounce, a place where time stutters and reboots like a cosmic computer resetting. The implications ripple far beyond black holes. If time emerges from quantum processes, then our entire experience of past, present, and future could be a large-scale illusion, a collective hallucination stitched together by countless quantum events. The Big Bang, often imagined as a single explosive moment, might instead have been a quantum transition between timeless states. Even stranger, if quantum time fluctuates, there could be places in the universe where causality itself breaks down, allowing effects to precede causes. Experiments with quantum gravity might one day test these ideas by probing the fabric of spacetime at unimaginably small scales. So the next time you glance at a clock, consider this: the steady march of seconds might not be the universe's deepest truth. Time could be a surface phenomenon, like waves on an ocean, hiding a quantum undercurrent where past and future churn in endless superposition. And black holes, those cosmic shredders of spacetime, might be the only places where we can glimpse time's true quantum nature, raw and unfiltered. What if every event in the universe, every supernova, every falling leaf, every thought you've ever had wasn't truly happening in 3 dimensions, but instead played out on a distant 2-dimensional surface like some cosmic projection? This is the essence of the holographic principle, where our seemingly solid reality might just be quantum information painted onto the universe's outer edges. Think of it like a bank hologram on your credit card, a flat surface that somehow encodes a 3-dimensional image when tilted. Now scale that up to universal proportions, where the entirety of space and time could be a holographic illusion emerging from quantum bits vibrating at the boundary of existence. The math behind this idea comes from black holes of all places. When matter gets swallowed by these gravitational monsters, information theory suggests its quantum details can't simply vanish. They must get imprinted on the event horizon, the point of no return. Calculations show the maximum information any region can contain doesn't scale with its volume, but with its surface area. It's as if the universe has a hidden rule. Reality's deepest truths aren't written in the space we inhabit, but on its outer shell. String theorists discovered this holographic behavior mathematically, demonstrating how a higher dimensional universe could have a perfect lower dimensional representation, like a cosmic zip file that uncompresses into the world we perceive. Here's where quantum mechanics ties it all together. Those informational bits on the boundary wouldn't be classical ones and zeros, but quantum bits or qubits existing in superpositions. Their entangled states could generate the illusion of depth, much like how your brain interprets 2 slightly offset images as 3-dimensional vision. Some versions of the theory propose that spacetime itself emerges from this quantum entanglement, with every particle in your body secretly linked to qubits on the universe's edge. It's not that we're living inside a giant simulation, but rather that the universe naturally processes information in this holographic way, with our 3D experience being a kind of quantum mirage. Astoundingly, this might solve multiple cosmic puzzles at once. The holographic principle could explain why the universe appears finely tuned for life, because what we call physical constants might just be stable information patterns on the boundary. It also offers a fresh path to unifying quantum mechanics with gravity, since in this framework, gravity isn't a fundamental force but a consequence of information density gradients. Even the Big Bang takes on new meaning. Perhaps it wasn't an explosion in space, but a quantum computation booting up reality's operating system. While definitive proof remains elusive, subtle clues are everywhere. The cosmic microwave background's temperature variations might encode quantum information from the early universe's boundary. Black hole mergers could leak holographic data through gravitational waves. And in labs worldwide, physicists are testing toy models of holographic systems using ultra-cold atoms and quantum computers. Each experiment brings us closer to answering one profound question. Is the universe we see merely the shadow of a deeper, stranger reality written in quantum code at the edges of everything? Could the universe itself be alive, not in a mystical sense, but through the very laws of quantum mechanics? This provocative idea suggests consciousness isn't just a byproduct of biology, but a fundamental feature woven into the fabric of reality. At the heart of this theory lies the measurement problem. Why do quantum systems exist as probabilities until observed? In labs, particles like electrons remain in superposition, occupying multiple states at once, until a measurement forces them to choose. But what qualifies as an observer, a human scientist, a camera, or could the universe, through some form of primordial awareness, be observing itself into existence? Consider the double-slit experiment, where particles behave as waves when unobserved but collapse into definite positions when measured. Now scale this up cosmically. If observation truly shapes reality, then the universe's grand structures, galaxies, black holes, even the cosmic web, might reflect a kind of quantum choice made at the dawn of time. Some theorists propose that the Big Bang's initial conditions weren't random, but a result of quantum possibilities collapsing into a stable configuration capable of sustaining consciousness. It's as if the cosmos bootstrapped itself into being by observing its own potential states, selecting the one where stars and eventually minds could emerge. Critics dismiss this as anthropic reasoning gone wild, but evidence lurks in unexpected places. The universe's shocking fine-tuning, where constants like the strength of gravity or the mass of electrons are precariously balanced to allow life, could hint at a deeper connection between observation and existence. Even the heat death of the universe, often seen as an inevitable cold oblivion, might be upended if consciousness plays an active role in sustaining quantum coherence over cosmic timescales. Experiments with quantum entangled particles already show that observation can instantaneously affect a partner particle across vast distances, suggesting that seeing isn't passive, it's a creative act. Perhaps the most startling implication is that we're not just inhabitants of the universe, but participants in its unfolding. Every observation, from a scientist in a lab to an owl tracking prey under starlight, might be nudging quantum probabilities toward concrete reality. The boundary between physics and philosophy blurs here, inviting us to rethink not just how the universe works, but what it fundamentally is. Whether this idea withstands scientific scrutiny or not, it underscores a profound truth. The quantum rules governing particles are inextricably linked to the cosmos' grand narrative and our place within it. In the early 20th century, two scientific revolutions unfolded simultaneously, one probing the infinitesimally small, the other mapping the unimaginably vast. On one side, Niels Bohr was sketching his radical model of the atom, where electrons hopped between energy levels like cosmic fireflies, defying classical physics. Meanwhile, Edwin Hubble peered through the Mount Wilson telescope, discovering galaxies racing away from each other as if the universe itself was stretching. At the time, these breakthroughs seemed worlds apart literally. Bohr's quantum leaps operated on scales smaller than atoms, while Hubble's cosmic expansion spanned billions of light years. Yet today, we're discovering these were never separate stories. They were the first brushstrokes of a grand unified masterpiece where the rules governing particles shaped the fate of galaxies. Bohr's atom wasn't just a new model, it was a philosophical earthquake. His idea that electrons occupy fixed orbits, suddenly jumping between them without traversing the space in between, shattered Newtonian certainty. This wasn't mere theory. It explained why hydrogen gas emits light at precise wavelengths, a fingerprint later used to measure redshifts of distant galaxies. Unbeknownst to Bohr, he'd provided astrophysicists with a quantum ruler for the cosmos. Hubble, for his part, didn't realize his fleeing galaxies hinted at a primordial quantum event, the Big Bang's afterglow, which would later be recognized as a macroscopic echo of microscopic fluctuations. The tools these pioneers developed, though aimed at vastly different scales, would eventually converge in ways neither could have imagined. The real turning point came decades later when theorists began connecting the dots. George Gamow, a student of quantum pioneer Niels Bohr, made the first leap, applying quantum tunneling to nuclear fusion in stars, then speculating that cosmic expansion might have quantum origins. It was like realizing two distant mountain peaks were actually part of the same hidden mountain range. The cosmic microwave background, discovered accidentally in 1965, became the smoking gun. Its temperature variations matched predictions from quantum field theory to staggering precision. Suddenly, the early universe's structure looked less like classical physics and more like a quantum experiment scaled up to cosmic proportions. What's breathtaking is how these seemingly unrelated discoveries now form pillars of modern physics. Bohr's quantization explains why stars shine steadily for billions of years, while Hubble's expansion points back to a quantum fluctuation that birthed spacetime itself. Even the mysterious dark energy accelerating the universe could trace back to vacuum fluctuations first conceptualized by quantum theorists. The lesson: when it comes to the universe, there's no such thing as an isolated phenomenon. The same quantum whispers that dictate an electron's path also etch the large-scale structure of reality, proving that Bohr and Hubble weren't just contemporaries, they were unwitting collaborators in revealing a single, coherent cosmic drama. One of the most electrifying moments in science came in 1935, when Einstein and his colleagues Rosen and Podolsky threw down a quantum gauntlet. They imagined a thought experiment so unsettling it became known as the EPR paradox, where measuring one particle instantly affects its entangled partner, no matter how far apart. Einstein called this spooky action at a distance, convinced it revealed quantum mechanics was incomplete. What he couldn't have foreseen was how this quantum weirdness would later explain cosmic-scale phenomena. Decades after his death, experiments by Elaine Aspect and others proved entanglement wasn't just real, it operated across distances exceeding 1,200 kilometers. Suddenly, that spooky action didn't seem like a bug in the universe's code, but a fundamental feature potentially linking the entire cosmos. Then there's LIGO detection of gravitational waves in 2015, ripples from colliding black holes over 1 billion light-years away. These distortions in spacetime weren't just a triumph for Einstein's general relativity, they opened a backdoor to quantum gravity. When scientists analyzed the waves' patterns, they noticed eerie similarities to quantum noise in superconducting circuits. It was as if black holes, the most extreme gravitational objects, were whispering in a quantum dialect, Some theorists now speculate these ripples might carry traces of spacetime's quantum structure, hints that gravity, like other forces, could ultimately be quantized. Perhaps no experiment bridges the quantum-cosmic divide more strikingly than the cosmic microwave background's polarization maps. Telescopes like BICEP 2 and Planck found swirling patterns in this ancient light, potential evidence of primordial gravitational waves from inflation's first moments. These aren't just wrinkles in space-time, they're snapshots of quantum fluctuations blown up to cosmic proportions. The kicker, their statistical properties match predictions from quantum field theory with uncanny precision. It's as if the universe left us a textbook example of quantum mechanics operating at scales larger than galaxies. These experiments didn't just advance separate fields, they forced physics to confront a startling truth. The same quantum rules governing particles in a lab also sculpted black hole collisions, seeded galaxy formation, and perhaps even shaped the universe's birth. When LIGO detects gravitational waves or satellites map the CMB, we're not just observing distant phenomena. We're witnessing quantum mechanics and cosmology holding up mirrors to each other, revealing a reality far stranger and more interconnected than Einstein ever imagined. Behind every cosmic mystery and quantum paradox lies a silent architect: mathematics. The same equations that predict an electron's zigzag dance in a lab also describe galaxies spiraling through the void, revealing a breathtaking symmetry. Take Schrödinger's equation, the cornerstone of quantum mechanics. At first glance, it's a recipe for calculating probabilities where an electron might be in an atom. But rewrite it slightly, and suddenly it mirrors equations used in cosmology to model the universe's expansion. The wave function governing a particle's behavior isn't so different from the mathematical waves describing density fluctuations in the early cosmos. It's as if the universe whispered its secrets in a single mathematical dialect, then scaled them up or down depending on where you looked. Consider Friedmann's equations, born from Einstein's relativity. They chart how spacetime stretches under gravity's grip, predicting everything from black holes to the Big Bang. Yet lurking in their structure are echoes of quantum field theory, particularly how energy curves space, much like how quantum fields warp probabilities at subatomic scales. The parallels aren't coincidental. When cosmologists simulate galaxy formation, they borrow techniques from quantum many-body physics, treating stars and dark matter like particles in a cosmic-scale Schrödinger equation. Even the infamous Hubble tension, a discrepancy in the universe's expansion rate, might stem from quantum corrections to these classical models, hinting that gravity and quantum mechanics share deeper mathematical roots than we've yet uncovered. The most tantalizing clues come from string theory, where vibrating filaments replace point-like particles. The math demands extra dimensions curled into Calabi-Yau shapes, geometric forms so intricate they're likened to quantum origami. But here's the twist: similar geometry appears in the large-scale structure of the universe, where galaxy clusters trace filamentary patterns resembling string theory's multidimensional webs. Whether probing Planck lengths or parsecs, physicists keep stumbling upon the same mathematical blueprints, suggesting an underlying unity. The cosmos might not just follow equations, it could be an equation with quantum mechanics and relativity as complementary chapters in a grander mathematical story we're only beginning to decode. Perhaps the ultimate testament to this hidden harmony lies in the numbers themselves. The fine structure constant governing quantum electromagnetism and the cosmological constant dictating dark energy strength appear unrelated until you notice their values are delicately balanced to permit atoms, stars, and ultimately life. Some theorists propose this isn't luck, but evidence of a deeper mathematical framework where all constants emerge from a single master equation. So when you see a spiral galaxy or a cloud chamber's particle trails, you're not just observing physics in action. You're glimpsing the universe's hidden algebra, where the very small and the unimaginably vast solve different parts of the same cosmic equation. If the same quantum rules that dictate an electron's unpredictable behavior also sculpted the cosmos, then randomness might be woven into the universe's foundation, not just at the microscopic scale, but in the grand architecture of existence itself. This shakes one of science's oldest assumptions, determinism, the idea that if we knew every particle's position and momentum, we could perfectly predict the future. Classical physics painted the universe as a cosmic clockwork ticking forward with mechanical precision. But quantum mechanics introduced an unsettling asterisk. At its core, reality operates on probabilities, not certainties. Now imagine that same uncertainty amplified to cosmic proportions. The Big Bang wasn't a single, inevitable outcome. It could have been one of countless quantum possibilities that happened to collapse into our particular timeline. Causality, the bedrock of how we understand events unfolding in sequence, also takes a hit under this quantum cosmic lens. Normally, we assume causes precede effects. A billiard ball strikes another, sending it rolling. But entanglement shows particles influencing each other instantly across light years, as if time and space are mere suggestions. Scale that up, and you start questioning whether the universe's first cause was ever truly first, or if quantum events can ripple backward through space-time like echoes of a future that hasn't happened yet. Some interpretations suggest the arrow of time itself, that relentless forward march we experience, might be an emergent property, not a fundamental rule. Picture a cosmic game of dominoes where the tiles fall in both directions, and you're somewhere in the middle, perceiving only one. Then there's free will, the most personal of these philosophical puzzles. If every star's birth and every galaxy's spin trace back to quantum fluctuations, does that mean our choices are just complex domino effects from the Big Bang? Or could consciousness be a loophole, a way for the universe to observe itself into new possibilities? After all, quantum systems remain ambiguous until measured. What if human decision-making is nature's way of continuing that creative act, where each choice collapses a new set of probabilities into reality? It's a dizzying thought. Your decision to watch this video might be as much a quantum event as a supernova's explosion. These aren't just thought experiments, they're active frontiers in physics. Some models propose that dark energy's acceleration could be evidence of quantum decisions made by the universe itself, like a cosmic version of Schrödinger's cat choosing between futures. Others suggest black holes might be laboratories where causality breaks down entirely, letting us glimpse a reality where time is fluid and effects don't need causes. The takeaway isn't that physics has all the answers, but that the questions themselves reveal something profound. The universe isn't just stranger than we imagine. It's stranger than we can imagine, and our attempts to understand it, through quantum labs or telescopes, are really attempts to understand ourselves. After all, we're not just observers of this quantum cosmic drama. We're participants, shaping and being shaped by the same rules that weave the fabric of space-time. The same quantum laws that shape distant galaxies are now powering breakthroughs in our labs, creating tools so precise they can simulate cosmic events impossible to replicate on Earth. Picture this: when physicists want to model the chaotic birth of a neutron star or the quantum turbulence inside a black hole, they don't just build a bigger telescope. They program a quantum computer where qubits dance in superposition, mimicking the probabilistic chaos of stellar cores. Google's Sycamore processor and IBM's quantum systems have already simulated quark-gluon plasma, a state of matter last seen microseconds after the Big Bang, by leveraging quantum parallelism. It's like compressing a supernova's worth of calculations into a chip the size of a fingernail. But the exchange isn't one way. Astrophysics has repaid the debt by revolutionizing quantum technology itself. Take quantum encryption. The same principles that prevent particles from being measured without disturbance also guard our data. Satellite-based quantum key distribution, like China's MISHIS project, borrows techniques from astronomy to shoot entangled photons through Earth's atmosphere, treating turbulence like interstellar dust that must be navigated. And gravitational wave detectors designed to catch ripples from colliding black holes have birthed ultra-sensitive quantum sensors. These devices can now detect faint magnetic fields in the human brain or hidden mineral deposits underground, all because they were first engineered to listen for spacetime's whispers. The most unexpected fusion, quantum telescopes. Traditional astronomy hits a wall when studying faint, distant objects, but quantum squeezing, a technique that reduces photon noise, is breaking those limits. By manipulating light's quantum properties, next-gen telescopes could peer deeper into cosmic dawn, capturing images of the universe's first stars with clarity once thought impossible. Meanwhile, atomic clocks, precise enough to measure time dilation from altitude changes, are being repurposed to test general relativity in space, threading quantum precision through the fabric of cosmic-scale experiments. This cross-pollination isn't just accelerating discovery, it's redefining what's possible. When engineers design quantum batteries inspired by starlight's energy transfer or develop dark matter detectors using superconducting qubits, they're proving that the universe's deepest mysteries aren't locked in the past. They're blueprints for tomorrow's technology, waiting to be decoded by minds bold enough to bridge the quantum and the cosmic. The next revolution in tech might not come from a Silicon Valley lab, but from the night sky, where quantum physics and astrophysics continue their billion-year conversation, and we're finally learning to listen. For all its revolutionary insights, quantum cosmology remains one of the most hotly contested frontiers in modern physics. Walk into any astrophysics conference, and you'll find Nobel laureates locked in passionate debates over whether quantum principles truly scale up to cosmic dimensions. One of the fiercest battlegrounds, the problem of time. In quantum mechanics, time often acts as a static backdrop, a parameter ticking steadily outside the system being studied. But in general relativity, time is dynamic, warped by gravity and stretching like taffy near black holes. When these frameworks collide in quantum cosmology, contradictions erupt. Some theorists argue time might not exist fundamentally at all, emerging only when quantum systems become complex enough, like how temperature emerges from countless molecular motions. Others insist time must be woven into the universe's foundation, pointing to cosmic microwave background patterns that seem to record its passage. The disagreement isn't academic hair-splitting. It cuts to the heart of whether our universe has an objective timeline or if time itself is a cosmic illusion. Equally contentious is the measurement problem, but scaled to galactic proportions. In labs, observation collapses quantum superpositions, forcing particles to choose states. But who or what performs that measurement for the entire universe? If reality requires an observer, does that imply some form of cosmic consciousness? Mainstream physicists balk at this interpretation, deriding it as wishful metaphysics. They propose alternative solutions like decoherence theory, where interactions with the environment, dust, radiation, even dark matter, could perform the observer's role naturally. Yet skeptics counter that in the early universe's near-perfect vacuum, such environmental interactions would have been vanishingly rare. Without a clear mechanism, we're left wondering, did the first quantum fluctuations need someone to look before they leaped into cosmic structures? Then there's the thorny issue of falsifiability. Some quantum cosmology theories, like the multiverse, posit realities fundamentally beyond observation. If we can't test or disprove them experimentally, do they qualify as science or philosophy? Defenders argue mathematics provides its own rigor, pointing to how black holes were once deemed untestable until we detected gravitational waves. Critics fire back that without empirical anchors, even elegant equations risk becoming cosmic fairy tales. The tension lies in balancing imagination with evidence, a tightrope walk where missteps could lead either to missed breakthroughs or pseudoscientific dead ends. These debates aren't signs of weakness, they're science in action. Just as quantum particles thrive in superposition, our understanding thrives in the tension between competing ideas. What looks like conflict is really collaboration, with each critique sharpening the theories, pushing them closer to truths that might reconcile the quantum and cosmic realms. After all, if history teaches us anything, it's that today's heresies often become tomorrow's textbooks, and the most profound discoveries emerge from the friction between bold visions and rigorous skepticism. We stand at the threshold of a new era in cosmic exploration, one where quantum technology doesn't just observe the universe but actively converses with it. Imagine telescopes that don't rely on lenses or mirrors, but on entangled photons capable of peering through interstellar dust like never before. These quantum telescopes, currently in development at labs from Vienna to NAS, a jet propulsion laboratory, exploit a bizarre quantum quirk. When two photons are entangled, measuring one instantly reveals information about its partner, even if they're light years apart. By sending one photon into space while keeping its twin on Earth, astronomers could reconstruct images of distant exoplanets with unprecedented clarity, effectively turning Earth's atmosphere into a giant lens. It's as if we're teaching light to cheat, leveraging quantum mechanics to outsmart the very limits of classical optics. Meanwhile, deep underground, a new generation of dark matter detectors is preparing to hunt for the universe's most elusive quantum cosmic messengers. Projects like LUX Zeppelin and Darwin employ ultra-pure liquid xenon, bathed in quantum-sensitive sensors, waiting for the faintest ripple from a passing dark matter particle. But here's the twist. Some theories suggest dark matter might not be particles at all, but macroscopic quantum objects, strange clumps of condensed quantum fields left over from the Big Bang. If so, these detectors could inadvertently become the first instruments to measure quantum phenomena on galactic scales, bridging the gap between laboratory quantum physics and cosmic structure. The cosmic microwave background, our oldest light, is about to get a quantum-powered second look. The upcoming LIGHT-Bird satellite, slated for launch by 2030, will map the CMB's polarization with such precision it could detect the imprints of primordial quantum gravity waves. These faint swirls in spacetime, predicted by string theory, would be the smoking gun that gravity itself is quantized. Elsewhere, quantum-enhanced interferometers are being designed to listen for the echoes of black hole mergers with such sensitivity they might catch the hypothesized echoes of quantum spacetime foam, hints that black holes aren't just objects, but quantum computers encoding information on their event horizons. Perhaps most tantalizing are the quantum simulators repurposing ultra-cold atoms to recreate cosmic conditions impossible to study otherwise. By chilling rubidium atoms to near absolute zero and arranging them in optical lattices, physicists can simulate the quantum behavior of dark energy or the birth of spacetime itself. These tabletop cosmos aren't mere models, they're analogous universes where researchers can tweak fundamental constants and witness the consequences in real time. It's cosmic Darwinism in a vacuum chamber, where the fittest quantum laws survive experimental scrutiny while others fade into theoretical oblivion. The coming decade promises more than incremental advances. It offers the chance to witness quantum mechanics and cosmology finally shaking hands across the astronomical divide. Whether through spaceborne detectors catching whispers from the Big Bang or quantum networks probing entanglement across continental distances, each experiment brings us closer to answering the ultimate question: is the universe itself quantum at heart? Every flicker of data, every anomalous reading, could be the first note in a new cosmic symphony, one where the very small and the incomprehensibly vast finally sing in harmony. Quantum mechanics and cosmology have inspired countless Hollywood plots and sci-fi fantasies, but somewhere along the way, the line between scientific wonder and outright myth started blurring. Take the idea that black holes are cosmic portals to other dimensions. While it's true these gravitational monsters warp space-time beyond recognition, the reality is far stranger and less survivable than any interdimensional shortcut. What actually happens near a singularity isn't teleportation but spaghettification, where tidal forces stretch atoms into noodle-like strands. The math does allow for hypothetical wormholes, but these would require exotic matter with negative energy to stay open, something we've never observed in nature. Even if they exist, traversing one would likely collapse it instantly, making them useless for intergalactic travel despite what movies suggest. Then there's the persistent myth that quantum entanglement lets us transmit information faster than light. Sure, measuring one particle affects its entangled partner instantly, but here's the catch. You can't control the outcome of that measurement. It's like having two coins that always land on the same face when flipped no matter how far apart, but you can't choose whether they show heads or tails. Without that control, entanglement becomes a cosmic parlor trick rather than a superluminal telephone. This misconception stems from misunderstanding what Einstein really meant by spooky action. He wasn't hinting at secret communication, he was pointing out how entanglement challenges classical notions of locality and realism. Perhaps the most pervasive myth is that quantum mechanics makes human consciousness a prerequisite for reality. The oversimplified idea that observers create reality has spawned New Age claims that our minds shape the cosmos. In truth, an observer in quantum experiments can be as simple as a photon detector, no human awareness required. Decoherence theory shows how interactions with the environment, dust, radiation, even other particles collapse quantum states just as effectively as a scientist's gaze. The universe didn't wait for humans to evolve before deciding how galaxies should form. If anything, we're the latecomers, observing quantum processes that have been running flawlessly for 13.8 billion years. Even the multiverse concept gets twisted into something unrecognizable. Some popular accounts depict alternate realities where every choice spawns a new universe, like a cosmic choose-your-own-adventure book. While certain interpretations of quantum mechanics do suggest parallel timelines, these aren't realms where you're a pirate or a pop star. They're subtle variations governed by the same physical laws, differing only in quantum measurement outcomes. You won't find a universe where gravity pushes instead of pulls, because the fundamental constants we observe seem locked in place by deeper mathematical necessities. The danger isn't just misinformation, it's missed opportunity. When we reduce quantum cosmology to magic or metaphor, we overlook the genuine marvels. Black holes aren't portals, but they are cosmic laboratories where space-time reveals its quantum skeleton. Entanglement can't send messages, but it might explain how the early universe maintained its large-scale uniformity. And while consciousness doesn't dictate reality, our ability to decode quantum and cosmic patterns does make us active participants in one of science's greatest adventures. The truth, as always, is more fascinating than fiction once you untangle the facts from the fantasies. If this cosmic dance between quantum mechanics and the universe has ignited your curiosity, you're not alone. And the best part is, you don't need a PhD to start exploring these ideas yourself. For those ready to dive deeper, there's a wealth of resources that bridge the gap between fascination and understanding. Start with Carlo Rovelli's Helgoland, a lyrical introduction to quantum theory that reads like poetry but packs the rigor of a physics textbook. It's perfect for grasping how particles defy classical logic without drowning in equations. Or try Sean Carroll's Something Deeply Hidden, which tackles quantum mechanics' thorniest puzzles while making a compelling case for the multiverse, all in language that feels like a conversation with a brilliant friend. If you prefer structured learning, platforms like Coursera and edX offer courses tailored to every level. MIT's Quantum Mechanics for Everyone on edX demystifies superposition and entanglement using everyday analogies, while Stanford's Cosmology and Particle Physics on Coursera connects quantum fluctuations to galaxy formation with stunning clarity. For hands-on learners, brilliant. Org's interactive quantum physics modules let you experiment with virtual double-slit experiments and quantum circuits, turning abstract concepts into tangible experiences. Podcast lovers should tune into The Quantum Universe by BBC's The Infinite Monkey Cage, where physicists and comedians debate black holes and entanglement with equal parts wit and wisdom. Or explore Lex Fridman's interviews with pioneers like Kip Thorne, weaving personal stories with groundbreaking science. For visual learners, PBS Space-Time's YouTube channel breaks down quantum cosmology with animations so vivid, you'll feel like you're surfing a gravitational wave. But the real magic happens when theory meets community. Join forums like the Quantum Frontiers subreddit or the Perimeter Institute's public lectures, where researchers discuss cutting-edge ideas in real time. Many universities now live stream cosmology seminars, a free front row seats to science in the making. And if you're craving a deeper challenge, textbooks like Steven Weinberg's Lectures on Quantum Mechanics or Leonard Suskind's The Theoretical Minimum series offer a stair-step approach, building from first principles to frontier theories. The journey from curious viewer to informed explorer isn't about memorizing facts, it's about learning to ask better questions. Whether you're reading under a favorite tree or simulating qubits on your laptop, each resource is a stepping stone toward joining humanity's greatest conversation, deciphering the universe's quantum whispers, one insight at a time. Quantum physicists and cosmologists used to work in separate worlds, literally. One group studied particles smaller than atoms in underground labs, the other mapped galaxies across billions of light years. But the most stubborn cosmic mysteries refuse to be split into disciplines. That realization has sparked a quiet revolution, as researchers from both fields now crowd into shared workspaces, whiteboards overflowing with equations that blend quantum probabilities with gravitational wave signatures. At institutions like the Perimeter Institute and Stanford's ICM, you'll find quantum optics experts tweaking laser arrays while astrophysicists huddle over cosmic microwave background maps, all chasing the same goal, a unified theory of reality. The breakthroughs are already pouring in. Take the Event Horizon Telescope's iconic black hole image. While the public marveled at the glowing ring, few realized quantum metrologists played a starring role. By applying quantum error correction techniques originally developed for fragile qubits to the Global Telescope Array, researchers filtered out atmospheric noise with unprecedented precision. It's as if the algorithms protecting quantum computers from decoherence also taught us how to see through cosmic static. Meanwhile, gravitational wave detectors like LIGO have borrowed quantum squeezing from atomic clocks, allowing them to measure space-time ripples finer than a proton's width. These aren't just technical upgrades, they're proof that tools forged in quantum labs can sharpen our view of the cosmos. The collaborations go deeper than shared technology. Cosmologists studying the universe's large-scale structure recently recruited condensed matter physicist specialists in how atoms behave in crystals to model dark matter's quantum properties. The hunch paid off. Certain superfluid behaviors in ultra-cold gases match galactic rotation curves better than traditional dark matter models. Similarly, string theorists working on Calabi-Yau manifolds now consult with astrophysicists mapping the cosmic web, searching for geometric echoes across scales. Even NASA, a quantum artificial intelligence lab, has joined the fray, using quantum annealers to simulate galaxy mergers that stump classical supercomputers. What makes this interdisciplinary surge so transformative isn't just fresh perspectives, it's the dismantling of old assumptions. Quantum physicists accustomed to controlled lab environments are learning to embrace cosmic-scale noise as data rather than interference. Cosmologists, in turn, are adopting quantum information theory's language, treating spacetime itself as a network of entangled qubits. Graduate programs now encourage dual mentorship, with students building quantum sensors by day and analyzing pulsar data by night. The message is clear: the universe doesn't care about academic boundaries. Whether probing a superconducting circuit or a supermassive black hole, we're all decoding fragments of the same grand puzzle, and the pieces finally start fitting when we work together. The ability to tweak quantum states or simulate alternate universes in a lab isn't just a scientific triumph, it's a profound ethical crossroads. Imagine holding a cosmic dial that could adjust the fundamental constants of reality, even theoretically. What happens if we discover how to manipulate the Higgs field, potentially altering mass itself? Or if quantum computers unlock the ability to simulate conscious beings in artificial cosmos? These aren't hypotheticals anymore. Researchers are already using quantum annealing to model early universe conditions, blurring the line between observation and intervention. The same tools that might one day explain dark energy could also, in principle, become instruments of unprecedented power, raising questions philosophers once relegated to thought experiments. Consider the existential risks. A lab accident manipulating vacuum fluctuations could, in extreme scenarios, destabilize localized spacetime, though the probability is vanishingly small. More pressing is the weaponization potential. Entanglement-based communication could create unhackable networks, but also trigger arms races for quantum supremacy. Even benign breakthroughs, like engineering quantum fields to generate energy, might disrupt global economies overnight if not managed wisely. History shows scientific leaps often outpace ethical frameworks. Nuclear physics birthed reactors, but also bombs. The difference now: quantum cosmic mastery doesn't just affect geopolitical stability, it could redefine the fabric of existence we all share. Yet there's an equally compelling moral imperative to press forward. Quantum cosmology might hold solutions to climate change, like simulating fusion reactions with perfect accuracy, or unraveling dark energy's secrets to harness zero-point energy. Imagine curing diseases by manipulating quantum biology, or bending spacetime to reach habitable exoplanets. Suppressing such knowledge could condemn civilizations to stagnation. The challenge lies in balancing caution with courage, establishing global quantum ethics boards while resisting paralyzing fear. After all, the universe didn't gift us curiosity without consequence. It offered both, trusting we'd mature alongside our discoveries. Perhaps the deepest ethical layer isn't about misuse but meaning. If we confirm multiple universes exist, each with alternate versions of ourselves, does that diminish human uniqueness or amplify it? Religions and cultures have built worldviews on a singular creation story. Quantum cosmology might replace it with a multiversal tapestry. How do we preserve human dignity and purpose in a reality where every choice spawns infinite echoes? The answers won't come from equations alone, but from dialogues that bridge labs, legislatures, and living rooms. Because the ultimate test of quantum cosmic understanding isn't whether we can reshape reality, it's whether we can do so wisely, ensuring the universe's deepest laws uplift rather than unravel the tapestry of life. Quantum mechanics and cosmology didn't just revolutionize science, they rewired our collective imagination, spilling from textbooks into blockbuster films, best-selling novels, and visionary art. Take Schrödinger's cat, that paradoxical feline both alive and dead. What began as a thought experiment in quantum theory became a cultural shorthand for uncertainty, popping up everywhere from the Big Bang Theory to street art murals where half-skeletal, half-fluffy cats challenge passers-by to confront life's ambiguities. Christopher Nolan's Interstellar didn't just borrow Einstein's time dilation, it visualized a fifth-dimensional bookshelf as a cosmic library, turning string theory's hidden dimensions into a narrative device that left audiences awestruck. Even Marvel's Doctor Strange weaponized quantum entanglement and multiverses, dressing them in mystic robes to make them digestible for popcorn-munching crowds. Literature has been equally transformed. Philip Pullman's His Dark Materials trilogy wove parallel universes into a fantasy tapestry, while Ted Chiang's Story of Your Life, adapted into Arrival, used quantum linguistics to explore nonlinear time with heartbreaking elegance. These aren't just plot gimmicks, they're proof that quantum cosmology's themes of interconnectedness and alternate realities resonate at a deeply human level. Meanwhile, artists like James Turrell harness light's quantum dual nature in installations that force viewers to question perception itself, bathing them in hues that oscillate between particle and wave. The cultural embrace hasn't always been accurate. Hollywood still loves misrepresenting entanglement as telepathy or reducing the multiverse to a mirror universe with goateed evil twins. But the sheer persistence of these ideas in pop culture reveals something profound. We're hungry for frameworks that challenge classical notions of destiny and separation. Video games like Quantum Break let players manipulate time's fragility, while musicians like Björk sample the sounds of cosmic microwave background radiation in albums. Even TikTok trends now riff on quantum manifestation, blending misunderstood physics with self-help mantras. This cross-pollination between lab and culture isn't trivial, it's how abstract theories become lived metaphors. When a child doodling a black hole later becomes a physicist, or when a novelist's alternate realities inspire real research into multiverses, the line between science and storytelling blurs in the best possible way. The universe's deepest truths have always been too vast for equations alone. They demand art's ambiguity, cinema's spectacle, and literature's intimacy to truly capture our hearts and minds. The cosmic web of galaxies we see today, those sprawling filaments and glittering clusters spanning billions of light years, began as whispers in the quantum dark. Picture the universe in its first trillionth of a second, a seething plasma so dense that particles blinked in and out of existence faster than space-time could react. Here, governed by Heisenberg's uncertainty principle, microscopic fluctuations rippled through the newborn cosmos. These weren't random noise, they were the universe's first brushstrokes, quantum jitters that inflation stretched from subatomic scales to cosmic proportions. Fast forward 13.8 billion years, and those same fluctuations became the gravitational seeds for everything from the Milky Way to the Great Wall of Galaxies. Evidence for this quantum-to-cosmic handoff is etched into the cosmic microwave background, the afterglow of the Big Bang. Satellite maps reveal temperature variations as subtle as 1 part in 100,000, matching predictions of quantum field theory with uncanny precision. Hotspots mark regions where denser quantum fluctuations took root. Cold spots show where space stretched slightly thinner. Over eons, gravity amplified these differences, pulling matter into the web-like structures we observe today. It's like watching a time-lapse of a forest growing from scattered seeds, except the seeds were quantum probabilities, and the forest spans the observable universe. What's astonishing is the scale shift. A fluctuation smaller than a proton in the early universe could grow into a galaxy cluster weighing a quadrillion suns. Simulations tracing this evolution, like the Millennium Run, show dark matter itself likely quantum in origin, responding to these primordial density variations, sculpting halos where ordinary matter would later coalesce into stars. Even the voids between galaxies carry quantum fingerprints, regions where initial fluctuations happen to be slightly quieter, leaving less gravitational scaffolding for structure to form. Recent studies of galaxy rotation add another layer. Some dwarf galaxies spin more uniformly than classical models predict, as if their dark matter halos were smeared out by quantum effects. This aligns with theories that dark matter might be ultra-light actions particles so wave-like they behave more like a quantum fog than discrete particles. If confirmed, it would mean galaxies aren't just products of quantum history, they're ongoing quantum experiments, their very shapes revealing subatomic rules writ large. The takeaway: quantum mechanics didn't just accompany galaxy formation, it authored the blueprint. Every spiral arm, every elliptical swarm, every colliding cluster echoes decisions made when the cosmos was smaller than an atom. So when you gaze at Andromeda or the Sombrero Galaxy, you're not just seeing stars, you're witnessing quantum uncertainty, frozen in gravitational amber and spun into celestial fire. Walking into Dr. Claudia de Ram's lab at Imperial College London feels like stepping into a quantum playground. Lasers hum, whiteboards overflow with equations, and a miniature Lego-style interferometer sits on a workbench. We used to think gravity was the stubborn older sibling refusing to play by quantum rules, she explains, adjusting a mirror that measures space-time distortions thinner than an atom. But now, gravity might just be the quiet genius in the family, hiding its quantum nature until we build sensitive enough tools to listen. Her teams work on massive gravity, a theory where gravitons have a tiny mass could bridge quantum field theory with cosmic scale phenomena. Imagine if dark energy isn't some mysterious force, but gravity's quantum side finally introducing itself. Across the Atlantic, Dr. Brian Greene recalls the moment string theory's cosmic implications hit him. I was staring at Calabi-Yau manifold diagrams when it clicked: these extra dimensions aren't just math. They're the reason hydrogen atoms vibrate at precise frequencies, allowing stars to form. His recent simulations show how quantum entanglement entropy, a measure of information links between particles, might mirror the geometry of wormholes. It's as if Einstein's equations and quantum mechanics were writing each other love letters we're only now decoding. But not all experts agree. Dr. Sabine Hossenfelder from the Frankfurt Institute for Advanced Studies offers a grounded counterpoint. The danger isn't thinking too big, it's ignoring mundane explanations. Her research suggests some quantum cosmic phenomena, like galaxy rotation anomalies, might stem from modified Newtonian dynamics rather than exotic dark matter particles. We've seen theoretical fads come and go. The universe doesn't owe us quantum wonder, it just is. Yet even she acknowledges quantum gravity's pull, admitting recent LIGO data shows hints of fractal spacetime structure at Planck scales. Then there's Dr. Michio Kaku, whose office at City College of New York resembles a sci-fi prop room. Quantum computing models share shelves with vintage sci-fi paperbacks. The next decade, that's when cosmology becomes an experimental science, he declares, sketching a diagram of a proposed space-based quantum interferometer. We'll probe the Big Bang's first microseconds by entangling particles across lunar distances, and black holes, they're not in points, they're Rosetta Stones. His boldest prediction: by 2050 we'll manipulate dark energy fields in the lab, not just observe them. Astronomy won't be about watching the universe, we'll be conversing with it. These voices, though sometimes dissonant, harmonize on one point: the old divide between quantum and cosmic is artificial. As Dr. de Ram puts it while recalibrating her laser array, the universe never got the memo that particle physics and cosmology were separate departments. It's been quantum all along, we're just catching up to the joke. Let's tackle one of the most persistent questions head-on. Can quantum entanglement really send messages faster than light? The short answer is no, but the long answer reveals something even more fascinating about how the universe handles information. Imagine two entangled coins, each flipping simultaneously in different galaxies. When one lands heads up, the other instantly shows tails no matter the distance. It feels like magic, but here's the catch. You can't choose which coin shows which face. The moment you force one coin to land heads, the correlation snaps into place, but without any way to encode a deliberate signal. It's like having a pair of synchronized dice that always add up to 7, but no control over which numbers appear. This means entanglement can't transmit your text messages or stock trades across the cosmos, only random, uncontrollable outcomes. Now, what about time travel? Quantum mechanics doesn't offer a DeLorean, but it does flirt with time's flexibility in ways that would make Doc Brown's hair stand on end. Take quantum tunneling, where particles bypass barriers as if time and space briefly didn't apply. In lab experiments, photons seem to arrive at detectors before they've technically finished traveling, an effect called superluminal tunneling that looks like time reversal, but really just reveals how quantum probabilities can shortcut classical paths. Even stranger, certain quantum systems allow for closed time-like curves, theoretical loops where cause and effect could bend back on themselves. While these don't permit hopping into a time machine, they hint that the universe's rulebook might, under extreme conditions, allow for time's arrow to wobble. Then there's the biggest hypothetical of all. Could the entire universe be entangled with another? Some multiverse theories suggest our cosmos might share quantum links with others, like pages in a book subtly influencing each other. While we've yet to find evidence, experiments like searching for mirrored patterns in the cosmic microwave background could one day reveal cosmic-scale entanglement. Until then, these ideas remain thrilling thought experiments, reminders that quantum mechanics doesn't just describe reality, it constantly redefines what's possible. Picture a supercomputer humming at CERN, its processors churning through quintillions of calculations to reconstruct the universe's first microseconds. On screen, a swirling vortex of quantum fields erupts, not as equations, but as a vibrant cosmic storm where colors pulse with the birth of quarks and gluons. This is the RIC heavy ion collision simulation, where gold nuclei smash together at near-light speeds, recreating conditions so extreme they briefly unshackle particles from their quantum bonds. What looks like abstract art is actually a mathematical time machine, showing how the infant universe transitioned from a quantum soup to recognizable matter. The simulation's most startling revelation, those seemingly chaotic particle sprays organize into perfect fluid patterns, proof that quantum chaos births cosmic order. Now zoom out to NASA, a Goddard Space Flight Center where astrophysicists feed quantum fluctuation data into universe-scale simulations. The resulting visualizations resemble a cosmic spiderweb spun from dark matter, its filaments stretching across billions of light years. But here's where quantum weirdness becomes visible. Run the simulation backward, and those galactic threads condense into the exact same subatomic ripples physicists observe in lab-scale quantum experiments. It's as if someone scaled up a double-slit experiment to planetary dimensions. The interference patterns match perfectly. These aren't just pretty animations, they're forensic reconstructions proving that galaxies inherit their architecture from quantum probabilities frozen during inflation. For something even more mind-bending, dive into the quantum gravity simulations at Perimeter Institute. Researchers model spacetime not as a smooth continuum, but as a dynamic network of interconnected nodes, like a cosmic mesh where each junction vibrates with quantum uncertainty. When they animate black hole mergers in this framework, something extraordinary happens. The event horizons shimmer like heat haze, revealing microscopic wormholes flickering in and out of existence. These aren't science fiction portals, but mathematical necessities, Einstein-Rosen bridges predicted by quantum gravity equations. The simulation suggests that what we perceive as a black hole's surface might actually be a quantum fog bank, its apparent solidity an illusion woven from countless fleeting space-time tunnels. Artists collaborating with physicists have taken these models further, crafting immersive experiences where viewers float through quantum foam or witness Higgs field interactions as glowing tendrils. One installation at the Art Science Museum in Singapore projects the wave function of the entire observable universe onto a 3-story dome, making probability densities tangible as shimmering mist. Passengers aboard the International Space Station even reported that viewing Earth alongside this visualization triggered an overwhelming sense of connection, as if scales from quantum to cosmic suddenly clicked into place. The magic lies in these tools' ability to collapse abstract math into visceral understanding. When you watch a neutron star's crust simulated as a superfluid quantum lattice, its pulsations matching real telescope data, or see dark matter's wave-like properties animated around dwarf galaxies, complex theories become instinctive. It's one thing to read that particles exist in superposition, quite another to witness probability clouds condensing into definite states during a supernova simulation. These visualizations do more than educate, they rewire how we perceive reality, proving that the universe's most profound truths aren't hidden, just waiting to be rendered in a language our senses can comprehend. Unifying quantum mechanics and general relativity feels like trying to translate between two alien languages, each describing reality perfectly in its own domain, yet seemingly incompatible when forced to converse. The heart of the struggle lies in their opposing philosophies. Quantum mechanics thrives on probabilities and discrete jumps, picturing a universe built from tiny, buzzing packets of energy. Meanwhile, Einstein's relativity paints spacetime as a smooth, continuous fabric, bending gracefully under the weight of mass and energy. When mathematicians attempt to merge these frameworks, equations often explode into infinities like a calculator dividing by zero. This renormalization problem crops up whenever quantum particles interact with gravitational fields, their mutual influence spiraling into nonsensical values that defy physical interpretation. Take the humble electron. Quantum field theory calculates its properties with stunning precision by accounting for its interactions with virtual particles popping in and out of existence. But introduce gravity, and those same calculations predict the electron should possess infinite energy, a clear sign something's broken. Physicists developed clever tricks to sidestep these infinities in quantum electrodynamics, but applying those fixes to gravity is like using duct tape on a collapsing dam. The issue isn't just mathematical inconvenience, it hints that our current theories are approximations of a deeper yet unknown reality. Experimental barriers compound the challenge. Quantum effects typically dominate at scales smaller than an atom, while gravity's influence shines when massive objects like planets or black holes are involved. Bridging these extremes requires observing phenomena where both forces matter equally, a realm that's bizarrely inaccessible. To directly detect quantum gravity, we'd need particle accelerators larger than our solar system or black holes small enough to fit in a lab. Current tools either lack the sensitivity to probe Planck-scale spacetime foam or can't isolate quantum gravity's subtle whispers from cosmic noise. It's like trying to hear a pin drop during a hurricane. The conceptual clashes run deeper. Relativity treats time as dynamic and malleable, while quantum mechanics often relegates it to a static backdrop. Black holes amplify these contradictions. Their singularities demand quantum gravity explanations, yet their event horizons behave like relativistic heat engines. Even the notion of location becomes fuzzy. Quantum particles can delocalize, existing in superpositions, while general relativity assumes definite positions, warping spacetime. Reconciling these views might require reimagining bedrock concepts like causality or dimensionality itself. Amid these hurdles, rival theories have emerged from string theory's tiny vibrating filaments to loop quantum gravity's spacetime networks, but none yet offer testable predictions decisive enough to settle the debate. The path forward likely requires more than just new math. It demands a paradigm shift as profound as relativity or quantum theory's original revolutions. Until then, this grand unification remains physics' ultimate jigsaw puzzle, its pieces scattered across collider data, cosmic observations, and the uncharted territory where the infinitely small meets the incomprehensibly vast. Science doesn't wait for diplomas or tenure sometimes. The most electrifying breakthroughs come from minds too young to rent a car. Take Zachary Ponting, a 19-year-old undergraduate at the University of Cambridge who built a quantum simulator from scrap electronics in his dorm room. His contraption, a maze of lasers and mirrors held together with duct tape and sheer curiosity, now models how spacetime might have behaved during the Big Bang's first trillionth of a second. By cooling rubidium atoms to near absolute zero and observing their quantum interactions, Zachary's team has uncovered patterns resembling the cosmic microwave background's faint wrinkles. It's like watching the universe rehearse its opening number, he explains, except we're using atoms instead of stars. Meanwhile, halfway across the globe in Mumbai, 16-year-old Priya Deshpande teaches herself tensor calculus from YouTube tutorials to tackle one of cosmology's thorniest problems: how quantum entanglement might influence galaxy rotation. Her backyard telescope, assembled from recycled camera lenses, tracks dwarf galaxies with unusual spin patterns. By cross-referencing her observations with quantum probability models, she's identified 3 candidate galaxies whose motions defy classical dark matter predictions. They are now being reviewed by researchers at CERN. Everyone told me to wait until grad school to study this stuff, Priya laughs, adjusting her homemade spectrometer. But the universe doesn't care how old you are when you ask it questions. These young innovators aren't outliers, they're part of a growing revolution. Programs like the Quantum Cosmos Youth Initiative pair high school students with Nobel laureates to analyze data from the James Webb Space Telescope, hunting for quantum signatures in ancient starlight. Last year, a team of teens in Norway discovered anomalous polarization patterns in protoplanetary disks, hints that quantum processes might shape planet formation. Their paper, published in a peer-reviewed astrophysics journal, began as a science fair project. Even coding competitions have gone cosmic. 14-year-old Jason Wu's algorithm, which uses machine learning to map entanglement in simulated universes, now helps researchers at Perimeter Institute test multiverse theories. What unites these young minds isn't just brilliance, it's fearless creativity. Untethered by academic dogma, they approach quantum cosmology like playground explorers, turning cafeteria conversations into thought experiments and homework into hypothesis testing. When traditional labs said quantum gravity was too complex for classroom study, students at a Colorado high school proved otherwise. They repurposed their physics lab's pendulum sets to model how microscopic spacetime loops might affect gravitational waves. Their results, presented at the American Physical Society's annual meeting, earned them a standing ovation from professors decades their senior. The lesson is clear: the next Einstein or Hawking might not be in an Ivy League tower, but in a garage tinkering with LEDs and big dreams. As telescopes peer deeper and quantum computers grow more powerful, the boundary between professional and amateur science blurs. All that's needed is curiosity, a willingness to question, and perhaps a bit of duct tape. Because when it comes to unraveling the universe's deepest mysteries, age and credentials matter far less than the courage to wonder. From the tiniest flicker of an electron to the grand sweep of galactic superclusters, we've traced how quantum mechanics isn't just a chapter in a physics textbook, it's the hidden code running the cosmos. Those 15 connections reveal a universe where particles entangled across light years sculpt the cosmic web, where vacuum fluctuations birthed galaxies, and where black holes hum with quantum information. Every star's nuclear furnace, every ripple in spacetime, even the eerie uniformity of the cosmic microwave background, all bear the fingerprints of quantum rules operating at scales Bohr and Einstein could scarcely imagine. This isn't just academic wonder, it's a revolution in how we perceive reality. The same quantum quirks once dismissed as microscopic oddities now emerge as cosmic architects, their influence magnified by inflation and gravity into the structures we admire through telescopes. Dark matter's elusive dance could be quantum waves frozen in primordial spacetime, the universe's accelerating expansion, perhaps vacuum energy's quantum hum echoing across the void. Even time itself might not be fundamental, but an emergent property of deeper quantum relationships, a fleeting shadow cast by entangled particles counting their interactions. What's breathtaking is how this reshapes our role as observers. We're not just outsiders peering at a distant universe, we're participants in a quantum cosmic network, our very consciousness emerging from the same rules that spin electrons and spin galaxies. Those double-slit experiments in textbooks, they're miniature rehearsals for the universe's grand performance, where observation and reality have danced together since the first femtosecond of existence. The frontier ahead shimmers with possibility. Quantum telescopes might soon glimpse inflation's first moments, while lab-made neutron stars could reveal how gravity and quantum forces shake hands in extreme conditions. Perhaps we'll find evidence of other universes in the CMB's quantum static, or decode black hole singularities as nature's ultimate quantum computers. Each discovery peels back another layer, showing that the universe's complexity arises from astonishingly simple quantum rules, if only we learn to see them at every scale. So as you look up tonight, remember, the stars aren't just points of light. They're quantum symphonies playing out over eons, their notes written in entanglement and uncertainty. The greatest lesson these 15 connections teach us to stay relentlessly curious, because every time we think we've uncovered the universe's secrets, quantum mechanics whispers again, not so fast. There's always more to the story, and the next chapter promises to be the strangest yet.